Picture this: a world not of rock or gas, but of pure, shimmering glass, floating silently in the void. Now, imagine the unimaginable: a neutron star, a cosmic heavyweight so dense that a single teaspoon of its material weighs as much as a mountain, hurtling toward this fragile gem of a planet. What happens when the universe's ultimate wrecking ball meets a world made of the most delicate substance imaginable? The collision would be unlike anything we've ever witnessed, a spectacle of destruction and beauty that bends the laws of physics to their breaking point. This isn't just science fiction, it's a thought experiment that reveals the extremes of our cosmos, where the ordinary rules no longer apply. Neutron stars are the remnants of massive stars that have exhausted their fuel and collapsed under their own gravity. They are so dense that their atomic structure is crushed into a sea of neutrons, packed tighter than the nucleus of an atom. And then there's the glass planet, a hypothetical world where sand, silica, and heat have fused into a vast, transparent sphere, reflecting the light of distant stars like a cosmic disco ball. Put these two together, and you have a recipe for chaos. The moment the neutron star's immense gravity reaches the glass planet, the surface would shatter like a dropped wine glass, sending glittering shards spiraling into space. But that's just the beginning. The real drama unfolds as the star's tidal forces stretch, compress, and ultimately vaporize the planet in a dazzling display of cosmic violence. Why does this matter? Because scenarios like this push our understanding of the universe to its limits. They force us to ask questions about the nature of matter, the behavior of extreme gravity, and the fleeting beauty of celestial destruction. This collision isn't just a fireworks show. It's a laboratory for some of the most bizarre physics imaginable, from the creation of exotic materials to the generation of gravitational waves that ripple through space-time itself. So buckle up. We're about to embark on a journey through one of space's most extreme hypothetical events, where the laws of physics are stretched to their absolute limits, and where the universe reminds us just how strange and wonderful it truly is. To grasp the sheer power of a neutron star, you have to think about what happens when a massive star dies. When a star many times heavier than our Sun runs out of fuel, it doesn't just fade away, it explodes in a supernova, one of the most violent events in the universe. What's left behind is a core so dense that atoms themselves collapse, squeezing protons and electrons together until they merge into neutrons. The result: a city-sized sphere with a mass greater than our entire Sun, spinning at dizzying speeds. Some of these neutron stars become pulsars, shooting out beams of radiation like cosmic lighthouses that sweep across space in precise, repeating pulses. But it's their gravity that truly defies comprehension. A single sugar cube's worth of neutron star material would weigh billions of tons more than Mount Everest. That's because the matter inside is packed so tightly that there's no empty space left, just a sea of neutrons crushed together. Their magnetic fields are equally extreme, trillions of times stronger than Earth's, capable of ripping apart atoms from thousands of kilometers away. When an object like this approaches a planet made of glass, the encounter isn't just a collision, it's a complete demolition. The neutron star's gravity would stretch and shatter the fragile glass world long before physical contact, turning its once pristine surface into a storm of glittering debris. Yet this destruction isn't just chaos, it's also a window into how matter behaves under the most extreme conditions. The way the glass fractures, melts, and vaporizes under a neutron star's pull could reveal secrets about exotic states of matter, from superfluid neutron cores to ultra-dense plasma. Even the debris field itself might briefly form strange new materials under the intense heat and pressure, like glass infused with neutron-rich elements never seen before. That's the paradox of neutron stars. They destroy, but they also create, reshaping everything they touch into something entirely new. A glass planet sounds like something straight out of a cosmic fairy tale, a world so pristine and fragile that it defies everything we know about planetary formation. Yet in the vast laboratory of the universe, where extreme conditions shape matter in ways we're only beginning to understand, such a place isn't entirely impossible. Picture a distant star system where temperatures and pressures align just right, allowing silica-rich materials to cool into a vast, transparent sphere. Unlike Earth's layered crust or Jupiter's swirling gases, this planet would be a single, brittle structure, more like a colossal marble than a traditional world. What would it look like from space? Sunlight striking its surface wouldn't just bounce off. It would refract, scatter, and dance through the planet's interior, creating a kaleidoscope of colors. Imagine a world that glows from within, its entire body acting like a lens, bending starlight into mesmerizing patterns. But this beauty comes at a cost. Without the internal strength of rock or the cushioning of an atmosphere, a glass planet would be extraordinarily vulnerable. Even a passing asteroid or the gravitational nudge of a nearby star could send cracks racing across its surface, turning it into a web of fractures waiting to shatter. And then there's the chemistry. Glass isn't just silicon and oxygen, it's a network of molecules frozen in place, without the orderly structure of crystals. On a planet-sized scale, this could lead to bizarre chemical behaviors. Trapped gases might form strange bubbles or veins, while extreme pressures deep within could create exotic forms of glass denser than diamond. Some scientists speculate that under the right conditions, a glass planet might even harbor traces of water or other volatiles locked inside its structure, like insects preserved in amber. But the most intriguing question isn't just how such a planet would form, it's how long it could last. In a universe where cosmic collisions and tidal forces are the norm, a glass world would be a fleeting wonder, a masterpiece of nature destined to meet a spectacular end. And that's exactly what makes the thought experiment so compelling. By imagining the extremes, we uncover the hidden rules that govern all planets, even the ones made of rock, gas, or ice. A glass planet may not exist, but the physics behind it is very real, reminding us that the universe is far stranger and more creative than we could ever invent. The moment the neutron star enters the glass planet's gravitational neighborhood, the laws of physics start playing a cruel game of tug-of-war. At first, the changes are subtle, a slight wobble in the planet's rotation, a faint tremor rippling through its crystalline surface. But as the distance shrinks, the star's gravity takes hold like an invisible hand, squeezing and stretching the fragile world into an egg-shaped nightmare. Imagine the entire planet bending like warm taffy, its glassy surface warping into jagged peaks and valleys miles high, each one glowing with stress fractures. These aren't mountains, they're fractures in the making, towering spires of glass trembling under forces no material could withstand. Then comes the light show. As the neutron star's magnetic field, trillions of times stronger than Earth's, brushes against the planet, it supercharges every atom in its path. Electrons are ripped from their molecules, creating rivers of charged particles that swirl across the surface. The result, auroras unlike anything in our solar system. Not just ribbons of color, but a searing, electric haze that dances across the sky in pulses of violet and gold. The entire planet becomes a lantern, its shattered landscape bathed in an otherworldly glow. But the real horror unfolds in slow motion. Unlike a quick collision, this is a drawn-out demolition where gravity does the dirty work. The side of the planet closest to the neutron star feels a pull so strong that glass flows like liquid, while the far side resists, still clinging to its original shape. This difference, the tidal force, keeps stretching the planet thinner and thinner until those once majestic glass spires crumble into glittering dust, avalanching into space. Long before the star makes physical contact, the planet is already coming apart at the seams, its fate written in the relentless pull of gravity. What makes this phase so fascinating isn't just the destruction, it's the physics at play. The way glass behaves under such extreme tension defies everyday intuition. On Earth, glass shatters instantly under stress, but here, the immense scale means fractures propagate in eerie slow motion, like cracks in a frozen lake spreading over hours. And those auroras, they're more than just pretty lights, they're a sign of the planet's very atoms being torn apart, ionized into plasma by the neutron star's magnetic wrath. This slow-motion unraveling also gives astronomers a hypothetical front-row seat to study tidal forces in action. On Earth, we only see their milder effects, ocean tides or the gentle flexing of moons. But here, the forces are so extreme they distort the planet's very structure, offering clues about how matter behaves when pushed beyond its limits. It's a cosmic lab experiment, one where the glass planet's destruction teaches us about the universe's most violent forces and the fleeting beauty that comes with them. As the neutron star closes in, its gravitational grip becomes unbearable. The glass planet, already stretched to its limit, can no longer hold itself together. This is tidal disruption, a cosmic demolition where gravity doesn't just crack the world apart, but peels it away layer by layer, like an onion unraveling in slow motion. The first signs are deceptively beautiful, vast sheets of glass, some the size of continents, lifting free from the surface as if in zero gravity. But this isn't gentle, it's chaos in crystalline form. The planet's brittle structure surrenders to the star's pull, fracturing along hidden fault lines with seismic shudders that would register across galaxies. What follows is a spectacle of destruction and light. Enormous shards, some towering hundreds of miles high, break loose and drift into space, catching starlight like a million shattered mirrors. But not all fragments meet the same fate. Those closest to the neutron star are vaporized in an instant, their silica-rich material flash heated into a glowing plasma. Others farther out are dragged into a deadly dance, spiraling inward to form a luminous accretion disk, a whirlpool of superheated glass and gas that orbits the star at nearly the speed of light. The friction within this disk is so intense that it radiates X-rays, painting the scene in high-energy light invisible to human eyes but blazing across the cosmos like a beacon. And then there's the gamma rays. When chunks of glass collide in the debris field or slam into the neutron star's surface, they release bursts of energy so powerful they outshine entire galaxies for a split second. These aren't just flashes, they're the universe's way of screaming, a testament to the raw violence of the encounter. For astronomers, these signals would be impossible to miss, a fireworks show of high-energy physics playing out in real time. Yet amid the carnage, there's eerie order. The debris doesn't scatter randomly, it follows the star's gravitational blueprint, swirling into intricate patterns dictated by relativity. Some fragments might even survive long enough to form transient rings or arc-like structures, their glassy surfaces reflecting the hellish glow of the accretion disk. It's a paradox, a scene of utter ruin, yet one sculpted by the precise laws of physics. This phase isn't just about destruction, it's a laboratory for the impossible. The temperatures and pressures in the accretion disk are so extreme that glass could behave in ways we've never seen, perhaps even forming exotic states of matter or brief, unstable compounds. And those X-rays and gamma rays, they carry fingerprints of the planet's composition, offering hypothetical scientists a way to study its makeup from light years away. Tidal disruption is a reminder that gravity isn't just a force, it's an artist, reshaping worlds with a brutality that borders on elegance. The glass planet's fate is sealed, but its demise illuminates the darkest corners of astrophysics, revealing how even the most fragile objects in the universe can teach us about its most unyielding laws. The moment the shattered glass debris spirals into the neutron star's grasp, the real fireworks begin. At these speeds close to the velocity of light, collisions aren't just impacts, they're transformations. Every shard, every grain of silica, slams into its neighbors with so much energy that the very concept of solid matter breaks down. Atoms are stripped bare, electrons torn away from their nuclei, and what was once a fragile glass world becomes a seething storm of plasma, hotter than the core of a star. This isn't just heat, it's a fundamental change in the state of matter, where the debris ceases to be solid, liquid, or gas and becomes a fourth state, a roiling, electrically charged soup of ions and free electrons, glowing with the intensity of a billion suns. But the neutron star isn't done sculpting this chaos. Its monstrous magnetic field, trillions of times stronger than Earth's, seizes control of the plasma, funneling it like water through a cosmic drain. The result, twin jets of supercharged particles erupting from the star's poles, shooting outward at nearly light speed. These aren't gentle streams, they're astrophysical blowtorches, narrow beams of energy so intense they can pierce through entire galaxies. From a distance, the scene would look like a celestial hourglass, with the neutron star at its waist and the jets stretching into the void, their tips glowing with X-rays and gamma rays. What makes these jets so extraordinary isn't just their power, it's their precision. Unlike the chaotic debris field, they're tightly focused, a testament to the neutron star's ability to impose order on chaos. The magnetic field acts like a particle accelerator, whipping the plasma into a frenzy and launching it with such force that it outshines entire star systems. For a brief, dazzling moment, this tiny remnant of a dead star becomes one of the brightest objects in the universe, a lighthouse visible across cosmic distances. And then there's the radiation. As the plasma churns and collides, it emits energy across the entire electromagnetic spectrum, from radio waves to gamma rays. Some of this light is so energetic it can't be seen by human eyes, but to telescopes, it's a treasure trove of data. Each wavelength tells a different part of the story. The infrared glow of cooling debris, the ultraviolet flare of recombining atoms, the X-ray scream of particles being crushed in the magnetic field. Together, they paint a portrait of destruction so vivid it's almost artistic. Yet amid this fury, there's a strange kind of creation. The plasma isn't just a byproduct of destruction, it's a crucible. In those fleeting moments of extreme heat and pressure, particles can fuse into elements that wouldn't form under normal conditions. Silicon might bond with oxygen in ways that defy chemistry textbooks, or neutrons might bombard nuclei, creating isotopes so unstable they decay in nanoseconds. It's a reminder that even in annihilation, the universe finds ways to experiment, to play with the building blocks of matter in ways we're only beginning to understand. This phase is more than just a spectacle, it's a masterclass in astrophysics. The way plasma behaves under such extreme conditions, the way magnetic fields can shape and direct it, even the way it radiates energy, all of it helps scientists unravel the mysteries of neutron stars, black holes, and the most energetic events in the cosmos. The glass planet may be gone, but in its final moments, it becomes a beacon, illuminating the darkest and most violent corners of the universe. the neutron star, now gorging itself on the shattered remains of the glass planet, enters a phase of cosmic gluttony. Every fragment pulled into its gravity well doesn't just vanish, it's assimilated, crushed into the star's already unimaginably dense structure. Think of it like a blacksmith hammering molten metal, each impact compressing the material further. But here, the hammer is gravity itself, and the anvil is a city-sized object with the mass of a sun. As the star feeds, its weight grows, and with it, the risk of crossing a critical threshold. Neutron stars exist in a precarious balance, their immense gravity held in check by a quantum force called neutron degeneracy pressure, which prevents total collapse. But add too much mass and even this fails. The star's core, overwhelmed, could implode in an instant, rewriting its destiny as a black hole. This feeding frenzy does more than just increase mass, it's a cosmic power-up. The incoming debris doesn't fall evenly. It spirals in, transferring angular momentum to the star like a whip cracking against a spinning top. The result? A dramatic speed boost. Neutron stars already rotate absurdly fast, some completing hundreds of revolutions per second. But under this torrent of material, the star's spin can skyrocket, transforming it into something even more extreme, a millisecond pulsar. These hyperfast remnants are the universe's natural particle accelerators, their magnetic fields whipping charged particles into beams so intense they slice across space like laser swords. What's fascinating isn't just the star's transformation, it's the window into stellar evolution. Normally, neutron stars fade quietly into the cosmic background, their spin slowing over eons. But here we see the opposite, a dead star reignited, its engines stoked by the destruction of another world. The process mirrors how some pulsars in our galaxy are thought to gain their incredible speed, likely from siphoning material from a companion star. Except in this case, the meal isn't a steady drip of gas, it's a full-course banquet of glass and plasma, served in a single, violent sitting. The aftermath of this feast leaves behind more than just a faster, heavier star. The energy released during accretion lights up the surrounding space, creating an X-ray glow detectable across interstellar distances. For astronomers, these signals are like cosmic breadcrumbs, revealing not just the presence of a neutron star, but its recent history. The composition of the ingested material, silicon, oxygen, traces of metals, might even alter the star's surface chemistry briefly, leaving spectral fingerprints before the intense gravity homogenizes everything into its neutron soup. Yet the most profound lesson here is one of limits. Neutron stars are nature's ultimate tightrope walkers, teetering between existence and oblivion. Their ability to consume and grow has a ceiling cross it, and they vanish from the visible universe, leaving behind only gravity's shadow. This stage isn't just about destruction or transformation. It's a reminder that even the most extreme objects in the cosmos play by rules we're still deciphering. And in that delicate balance between star and black hole, we find clues to some of astrophysics' deepest mysteries, from the fate of matter under infinite pressure to the birth cries of the universe's most enigmatic objects. The destruction of the glass planet isn't the end, it's the beginning of a cosmic detective story written in light. As the last shards vaporize in the neutron star's fury, they don't just disappear, they transform into a radiant fingerprint, a spectral signature as unique as a chemical barcode. Glass, when superheated to millions of degrees, doesn't glow like ordinary matter. Silicon and oxygen atoms, ripped apart and reassembled in the plasma maelstrom, emit light at wavelengths so distinct they'd stand out against even the brightest cosmic backgrounds. To astronomers, these telltale signals would be like finding a neon sign in a desert, impossible to miss and packed with information. What makes this aftermath so valuable isn't just the spectacle, it's the data. The neutron star's extreme environment acts like a particle accelerator the size of a solar system, creating conditions so harsh they turn vaporized glass into a physics playground. Under normal circumstances, silica breaks down long before reaching these temperatures, but here, crushed by pressures billions of times greater than Earth's core and bombarded by radiation, it behaves in ways that challenge our understanding of matter itself. Atoms might form brief, exotic configurations, perhaps temporary alliances between silicon and neutrons, or oxygen atoms squeezed into bizarre, flattened shapes by the star's ridiculous gravity. These extreme states aren't just theoretical curiosities. They mirror conditions believed to exist in the early universe, moments after the Big Bang when matter was too hot and dense to form stable atoms. By studying how glass behaves in this neutron star crucible, scientists could catch glimpses of physics that haven't existed naturally for over 13 billion years. It's like finding a cosmic time capsule, one that only reveals its secrets under the most violent circumstances. And then there's the broader implication, the echoes this event leaves across the cosmos. The spectral lines from vaporized glass wouldn't just fade into noise. They'd travel through space, potentially for millions of years, carrying encoded information about the collision. Future civilizations, or our own astronomers with more advanced tools, might decode these signals to reconstruct the entire catastrophe long after the neutron star has moved on. This is how the universe communicates, not in words, but in light and energy, telling stories of destruction and rebirth across unimaginable distances. The real treasure lies in what this means for other cosmic mysteries. If we can recognize the spectral signature of vaporized glass around a neutron star, could we spot similar traces elsewhere? Might we find evidence of stranger worlds, planets made of diamond or ice or even more exotic materials, by their unique light fingerprints when torn apart by black holes or colliding stars? This single hypothetical event opens a door to understanding how all kinds of unusual celestial bodies meet their ends and what they leave behind in their final moments. What begins as a cataclysm ends as a revelation. The glass planet's demise is more than just a fireworks show. It's a fleeting opportunity to witness the universe's most extreme physics in action. Its spectral afterglow becomes a textbook written in plasma, a temporary but brilliant record of how matter behaves when pushed beyond all limits. And in that brief, luminous aftermath, we're reminded that even in destruction, the cosmos finds ways to teach, to reveal, and to astonish. The collision doesn't just tear apart the glass planet, it warps the very fabric of reality. When a neutron star's immense gravity tangles with the planet's fragile structure, the resulting chaos sends shockwaves through space-time itself. These aren't ordinary waves like ripples on a pond, they're gravitational waves, distortions in the cosmic grid predicted by Einstein over a century ago. Picture dropping a boulder into a still lake, except the lake is the universe, and the boulder is a city-sized object with the mass of a sun slamming into a world made of glass. The energy released is so colossal that it literally bends the dimension of time, compressing and stretching space as the waves radiate outward at the speed of light. What makes these waves so special isn't just their existence, it's what they carry. Every ripple encodes a forensic record of the collision, from the neutron star's spin to the glass planet's final moments. The wave's frequency, amplitude, and shape tell a story: how the planet fractured, how debris spiraled inward, even how the neutron star's surface trembled under the impact. It's like listening to a cosmic opera where every note reveals another layer of physics. When scientists detect gravitational waves from merging black holes or neutron stars, they're not just hearing a thud, they're decoding an entire symphony of destruction. Detecting these particular waves would be a landmark event. Current observatories like LIGO and Virgo are tuned to catch collisions between dense objects like black holes or neutron star pairs. But a neutron star meeting a glass planet, that's uncharted territory. The event would produce a unique waveform, a sharp, chaotic crescendo as the planet shatters, followed by a rapid decay as debris is consumed. Unlike the clean chirp of two neutron stars merging, this signal would be messy, asymmetrical, and packed with clues about how unusual materials behave under extreme gravity. It might even reveal surprises, like whether fragments of the glass planet briefly orbited the neutron star before being shredded, creating secondary ripples in the signal. Beyond confirmation, these waves could answer bigger questions. How much energy does it take to utterly vaporize a planet? What happens to solid matter when tidal forces exceed the strength of atomic bonds? Gravitational waves from this event would carry those numbers etched into their very structure, offering data no telescope could collect. They might even hint at whether similar collisions happen elsewhere in the universe, suggesting that glass planets or other exotic worlds might be more common than we thought. The most profound implication isn't about destruction, it's about connection. Gravitational waves link us directly to the event, carrying information untouched by millions of years of travel through space. The light we see is delayed, filtered through dust and gas, but these waves arrive pristine, a direct line to the physics of the catastrophe. In a way, they're the universe's purest messengers, delivering truths about neutron stars, planetary limits, and the nature of gravity itself, truths that might one day rewrite our understanding of the cosmos. The universe never truly wastes anything, not even the glittering wreckage of a shattered glass planet. As the neutron star moves on, its gravitational wake leaves behind more than just empty space. The debris field, now cooled from its plasma state, begins a slow dance of cosmic recycling. Some fragments, flung outward at high speeds, escape the star's pull entirely, becoming rogue asteroids of pure glass, tumbling through the void like celestial marbles. Others, trapped in wider orbits, might clump together over millennia, their surfaces fused by micrometeorite impacts and radiation. Given enough time and the right conditions, these glassy remnants could become the building blocks of entirely new worlds. This isn't just theoretical. We've seen hints of this process in our own solar system. Take silica-rich asteroids or the glassy spherules found in lunar soil, forged by ancient impacts. These real-world examples show how extreme events can reshape matter into unexpected forms. Now, imagine that on a galactic scale, a future where shards from our doomed glass planet collide, stick together, and grow. First into boulders, then moonlets, and perhaps, given billions of years, into a new generation of planets. These wouldn't be exact replicas of their predecessor. Without the delicate conditions that birthed the original glass world, they might form hybrid bodies, rocky cores wrapped in glassy crusts, or layers of crystalline and metallic materials forged in the neutron star's fury. But the recycling goes deeper than just physical reassembly. The destruction of the glass planet injects rare elements into the interstellar medium. Silicon, oxygen, and trace metals, once locked in a fragile sphere, now disperse as fine dust or gas clouds. Over cosmic timescales, these materials will mix with molecular clouds, the nurseries of new stars and planets. Future stellar systems might incorporate these atoms into their own worlds, perhaps even forming glassy minerals in their crusts or atmospheres. It's a poetic twist, the remnants of one catastrophe becoming the ingredients for another's birth. The most fascinating aspect of this recycling isn't the materials, it's the energy balance. The neutron star's feast releases enough radiation to ionize nearby gas clouds, triggering star formation in regions that might otherwise have remained dormant. Like a cosmic domino effect, the death of one object sparks the birth of others. This interplay between destruction and creation is fundamental to the universe's evolution. Supernova-enriched galaxies with heavy elements, colliding neutron stars seed space with gold and platinum. And now, in our thought experiment, a glass planet's demise contributes to the cycle in its own unique way. What does this mean for the broader cosmos? It suggests that even the most cataclysmic events are part of a grand, self-sustaining system. Planets, stars, and galaxies don't exist in isolation. They're linked by flows of matter and energy, each catastrophe feeding the next genesis. A glass planet's destruction might seem like an endpoint, but in reality, it's a transformation, a step in an endless loop where every ending is also a beginning. And that's the ultimate lesson. In space, nothing is ever truly lost. It's just waiting to become something new. Could a planet made of glass ever cradle life? It's a question that stretches our imagination to the breaking point. Picture a world where the ground beneath your feet isn't soil or rock, but a vast, transparent slab, where sunlight doesn't just warm the surface but penetrates deep into the planet's core, refracting into blinding rainbows. The very qualities that make a glass planet mesmerizing also make it a nightmare for life as we know it. Without the insulating layers of rock or the heat-trapping embrace of an atmosphere, temperatures would swing violently between scorching daylight zones and frigid shadows. The planet's brittle structure would groan under its own weight, riddled with cracks and fissures that could split open without warning, venting any trapped gases into space. Yet life, if it existed here, wouldn't play by Earth's rules. Imagine organisms evolved to thrive in crystalline lattices, their biology built around silicon instead of carbon, their cells structured like microscopic stained glass windows. These wouldn't be creatures that crawl or swim. They might pulse with light, harvesting energy directly from the refracted rays piercing their glassy habitat. Their bodies could be self-repairing, fusing fractures with secretions that harden like molten silica. Some might even migrate across the planet's surface, following the shifting patterns of sunlight like living solar panels. But the real challenge isn't just surviving, it's reproducing. On Earth, life spreads through water, wind, or movement. Here, propagation might rely on the planet's fragility. Organisms could disperse their offspring through shattering events, sending glass-encased spores skittering across the surface during quakes, or even catapulting them into space during meteor strikes. It's a haunting thought. Life clinging to existence not despite the planet's instability, but because of it, turning destruction into a survival strategy. The neutron star's arrival, however, would rewrite every rule. Long before impact, its gravity would destabilize the planet's delicate equilibrium. The same tidal forces that stretch and shatter the glass would obliterate any ecosystems trapped within. Radiation from the star's magnetic field would sterilize the surface, stripping molecules apart atom by atom. And as the planet fractures, any life forms, no matter how adapted, would face temperatures hotter than stars, pressures that crush silica into neutron-rich slurry, and a final, inescapable truth. In the face of such cosmic violence, even the hardiest life has limits. This isn't just a thought experiment about extinction, it's a lesson in planetary fragility. A glass world, for all its beauty, would be a fleeting sanctuary. Its hypothetical life forms a testament to the ingenuity of biology and the ruthlessness of the universe. The collision reminds us that while life might find footholds in the strangest places, some environments are too extreme, too transient, to offer more than a momentary spark before the cosmos snuffs it out. And yet, in that brief window, the idea of glass-dwelling life challenges us to rethink what's possible. pushing astrobiology to imagine life not as we know it, but as the universe might dare to create it. Detecting a collision between a glass planet and a neutron star would push our observational tools to their absolute limits. Unlike rocky or icy worlds that reflect and absorb light predictably, a glass planet is nearly transparent, its surface bending and scattering light in ways that make it almost invisible against the blackness of space. Even the most powerful optical telescopes might miss it entirely, registering only faint distortions in the starlight passing through its crystalline structure. By the time we'd notice something unusual, perhaps a shimmering anomaly in the darkness, the neutron star's gravity would already be shredding the planet apart, turning it from a stealthy wanderer into a blazing spectacle of destruction. The real challenge lies in timing. These events unfold incredibly fast by cosmic standards, from the first gravitational tremors to the final vaporization of the planet's remains. The entire catastrophe might span mere hours, far too brief for traditional sky surveys to catch unless we're already looking in the right direction. That's where gravitational wave detectors like LIGO and Virgo become invaluable. Unlike light, gravitational waves can't be obscured by dust or dimmed by distance. They'd carry the unmistakable signature of the collision, a chaotic ripple in spacetime that stands out from the cleaner signals of black hole mergers or neutron star binaries. Even then, pinpointing the exact source would require a coordinated effort, with observatories across the electromagnetic spectrum scrambling to train their instruments on the event before it fades. Infrared telescopes might offer our best shot at spotting the aftermath. As the glass shards vaporize, they'd release heat in telltale wavelength, silicon and oxygen atoms glowing in the infrared like embers from a cosmic forge. The neutron star's accretion disk, superheated to millions of degrees, would emit X-rays detectable by orbiting observatories like Chandra or the upcoming Athena mission. But perhaps the most revealing clues would come from spectroscopy. The light passing through the debris field would carry chemical fingerprints, revealing not just the presence of vaporized glass, but also the exotic compounds forged in the collision's extreme conditions. Yet, even with all these tools, luck plays a huge role. The universe is vast, and such events are staggeringly rare. We'd need the collision to happen relatively close, within a few 100 million light-years, for our instruments to catch the details. And even then, the data would raise as many questions as answers. How much of the glass planet survived as debris? Did any fragments escape the neutron star's pull? What new materials formed in the chaos? Each observation would be a snapshot of a fleeting moment, a single frame in a cosmic movie we're only beginning to understand. This isn't just about spotting a cataclysm, it's about testing the limits of our technology and imagination. The search for such an event forces us to rethink how we observe the universe, pushing detectors to new sensitivities and inspiring tools we haven't even invented yet. In a way, the difficulty of detection makes the quest even more compelling. It reminds us that the cosmos still holds mysteries that defy our current vision, and that every breakthrough begins with asking, what are we missing? To recreate this cosmic catastrophe in a supercomputer, scientists face a puzzle of staggering complexity. The simulation must juggle three brutal forces: the glass planet's brittle fragility, the neutron star's crushing gravity, and the plasma tornado that forms in their wake. Each factor defies conventional physics. Glass doesn't just crack under pressure, it fractures in intricate webs with stress lines branching like lightning at microscopic scales. Neutron star gravity isn't a steady pull. It's a tidal sledgehammer varying wildly across the planet's width, and the resulting plasma. It's a quantum soup where magnetic fields twist particles into spirals hotter than supernova. Modeling this demands more than raw computing power. It requires rewriting the rulebook on how matter behaves at extremes. The process starts with data from real-world analogs. Researchers feed the software with lab experiments where lasers shatter ultra-pure silica, mimicking the planet's composition. Telescopic observations of neutrons, stars, their spins, magnetic fields, even the X-ray whispers of their accretion disks provide boundary conditions. But the magic happens when these datasets collide inside the simulation. Supercomputers like Frontier or Fugaku divide the glass planet into billions of virtual fragments, each governed by equations that predict how it will bend, snap, or vaporize under the neutron star's pull. The calculations are so precise they track individual atoms at the fracture fronts, where glass transitions from solid to dust to ionized gas in nanoseconds. What emerges isn't just a video, it's a revelation. The simulations reveal surprises no theorist could intuit. For instance, glass doesn't just shatter uniformly. Vast sheets peel away in curved planes like bark from a cosmic tree before disintegrating into diamond-shaped shards. The debris doesn't spiral inward smoothly. It clumps into transient rings like Saturn's rings forged in a furnace, which then fragment into arcs under magnetic stresses. Most strikingly, the plasma jets fired from the neutron star's poles aren't steady. They pulse in rhythm with the planet's destruction, as if the star itself is screaming in gravitational waves. These virtual experiments do more than satisfy curiosity. They guide real-world observation. By predicting the collision's light signatures, from infrared glows of cooling glass to gamma-ray spikes from particle collisions, the models tell astronomers where and how to look. When the Vera Rubin Observatory scans the sky nightly, its algorithms can now search for these specific flickers. Gravitational wave detectors, primed with frequency profiles from the simulations, might someday catch the unique crunch of a glass world meeting its end. Yet the grandest insight isn't about this specific catastrophe, it's about the limits of matter itself. The simulations expose gaps in our understanding of material science. Under neutron star-level stresses, glass behaves neither as a solid nor a liquid, but as something in between, a state that could hint at new physics. Plasma turbulence in the debris disk forms patterns seen nowhere else, suggesting exotic forms of conductivity. Every failed simulation, every time the virtual planet breaks wrong, is a clue that our equations are incomplete, pointing researchers toward discoveries waiting in the extremes. This digital laboratory proves that even the most outlandish cosmic scenarios can sharpen our view of reality. By pushing silicon to its limits in ones and zeros, we prepare for the day, if it ever comes, when telescopes catch the real thing. And until then, these simulations stand as monuments to human ingenuity, a species that can destroy worlds inside machines just to learn how the universe builds them. The universe gave us a glimpse of neutron star violence in 2017, when gravitational wave detectors caught the aftermath of two colliding stellar corpses. Known as GW170817, this event wasn't just a scientific milestone, it was a cosmic Rosetta Stone, decoding how these ultra-dense objects interact. But comparing that real-world merger to our hypothetical glass planet scenario is like contrasting a controlled demolition with a fireworks factory explosion. Both involve destruction, but the ingredients and outcomes couldn't be more different. When those two neutron stars spiraled together, they created a kilonova, an explosion 1,000 times brighter than a typical nova. The debris was packed with heavy elements like gold, platinum, and uranium, forged in the extreme conditions of the collision. Spectroscopic analysis revealed signatures of rapid neutron capture, a process where atomic nuclei gulp down free neutrons like cosmic Pac-Men, transforming into heavier elements almost instantly. But a glass planet's demise would paint a very different picture. Instead of metal-rich debris, we'd see spectral lines screaming with silicon and oxygen, the telltale fingerprints of vaporized glass. The kilonova's traditional gold rush would be replaced by a shimmering storm of silica dust, glowing in infrared like a billion tiny prisms. Energy release tells another diverging story. The neutron star merger unleashed gravitational waves equivalent to the power output of every star in the observable universe for 30 seconds. Yet our glass planet scenario trades that concentrated punch for prolonged pyrotechnics. The tidal disruption phase stretches energy release over hours or days, like a cosmic slow burn. Instead of a single gamma-ray burst, we'd witness a cascading light show X-ray flares from the accretion disk, ultraviolet pulses from superheated glass plasma, and optical flashes as debris fragments collide. It's the difference between a lightning strike and a forest fire, both dazzling but operating on entirely different timelines. The aftermath also diverges dramatically. GW 170817 left behind either a heavier neutron star or a fledgling black hole, surrounded by a debris field rich in our process elements. But a glass planet's remnants would create something far stranger, a neutron star wrapped in a temporary silica shroud, its magnetic fields threading through glassy plasma like needles through molten lace. Over time, this material might condense into exotic glass-ceramic hybrids, materials with structures that don't exist naturally anywhere else in the cosmos. What makes these comparisons invaluable isn't just academic curiosity, it's about calibrating our cosmic intuition. By studying how real neutron star mergers unfold, we gain reference points to test our hypotheticals against. When future observatories detect unexplained infrared glows or odd gravitational wave signatures, the glass planet scenario becomes one more tool in our interpretive toolbox. The universe has shown us it's capable of collisions beyond our wildest imagination, so why not one where a star meets a world made of glass? The moment the glass planet fractures under the neutron star's gravitational assault, an invisible force takes center stage: magnetism. Neutron stars don't just crush matter, they command it with magnetic fields so powerful they could strip data from every hard drive on Earth from 1,000 light-years away. When these fields meet the vaporized remains of a glass world, chaos transforms into eerie order. Superheated plasma, which should scatter randomly, is instead funneled into precise pathways like water forced through the grooves of a cosmic record. The star's poles become particle accelerators, launching jets of charged material at near light speed, while its equator wraps the debris into a shimmering disk, its rotation synced to the star's dizzying spin. But this magnetic choreography isn't just for show. It dictates the collision's entire aftermath. The star's field acts like a cosmic sculptor, determining which debris escapes as glowing jets and which spirals inward to feed the star's growth. In some regions, magnetic pressure overrides gravity, creating temporary bubbles where glass plasma lingers longer than physics should allow. Elsewhere, field lines twist into knots, sparking bursts of X-rays as they snap and reconnect, a process seen in solar flares but amplified to universe-shaking intensity. The star's spin adds another layer of complexity. As it gorges on glassy debris, the incoming material transfers angular momentum, like a figure skater pulling in their arms to spin faster. But the magnetic field resists this acceleration, acting as a cosmic brake. The resulting tug of war can trigger starquakes, sudden cracks in the neutron star's crust that release energy equivalent to 1 billion atomic bombs. These quakes ripple through the debris field, shaking loose trapped particles and sending fresh surges of plasma spiraling down magnetic highways. What makes this interplay so vital to understand? Because magnetic fields are the universe's hidden architects, They shape everything from newborn stars to galaxy-spanning jets. By studying how they mold the glass planet's remains, we glimpse fundamental processes that power quasars, gamma-ray bursts, and other cosmic heavyweights. The data encoded in those plasma jets, their temperature, composition, and polarization, could reveal secrets about how matter behaves when magnetism, not gravity, calls the shots. Ultimately, this stage isn't just about destruction, it's about transformation. The same forces that tear the glass planet apart also forge its debris into something new, a fleeting laboratory where the universe's most extreme magnetism writes its rules in light and plasma. And for astronomers, that's the real treasure, a chance to witness physics pushed beyond textbooks, where the ordinary becomes extraordinary and the impossible becomes routine. The collision unleashes a light show so brilliant it would redefine our understanding of cosmic fireworks. As the neutron star's gravity shreds the glass planet, trillions of shards explode outward, each acting like a celestial prism. Sunlight refracts through these spinning fragments, splitting into rainbows that stretch across light years, a kaleidoscope of color brighter than 1,000 supernovae. But this is just the opening act. The real spectacle begins when the star's magnetic field seizes control, whipping the vaporized glass into plasma jets that blaze across the electromagnetic spectrum. X-rays scream from the accretion disk's inner edge, ultraviolet pulses flare as atoms recombine, and optical light bursts forth as debris collides, creating flashes visible to the naked eye from another galaxy. What makes this display unique isn't just its brightness, it's the choreography. Unlike a supernova's chaotic explosion or a quasar's steady glare, this event unfolds in layers. First, the silent ballet of fracturing glass, its stress lines glowing with trapped starlight. Then, the plasma's violent tango as it spirals into the disk, heating until it emits gamma rays potent enough to pierce through dust clouds. Finally, the grand finale, twin jets erupting from the neutron star's poles, their particle beams interacting with interstellar gas to produce shimmering shockwaves. The result is a light show with rhythm, a cosmic symphony where each wavelength plays its part. The colors tell a story no telescope could ignore. Silica vapor emits a signature turquoise glow at specific infrared wavelengths, while ionized oxygen paints the debris field in crimson and gold. These hues aren't just pretty, they're data. Astronomers could read them like a barcode, revealing the planet's composition, the collision's energy, even the neutron star's spin. And because glass refracts light so cleanly, the event would create lensing effects, bending background starlight into temporary rings and arcs, a fleeting cosmic mirage. Yet the most astonishing detail might be the shadows. Dense clusters of glass debris cast stark silhouettes against the glowing plasma, creating moving patterns like clouds eclipsing the sun. These shadows aren't static, they ripple outward at relativistic speeds, stretching and compressing as the neutron star's gravity warps space-time around them. For a brief moment, the universe becomes a shadow puppet theater with the laws of physics pulling the strings. This isn't just destruction, it's art. A display where every photon carries information about the extremes of matter, magnetism, and gravity. And while the show might last only hours, its light would travel for eons, a postcard from the edge of physics waiting to be decoded by whoever or whatever finds it next. The energy unleashed when a neutron star consumes a glass planet doesn't just break records, it rewrites the cosmic rulebook. Picture all the sunlight Earth has received since the dawn of civilization, concentrated into a single second. Now multiply that by a factor beyond counting. This collision converts an entire planet's mass directly into energy through Einstein's most famous equation, E equals mc squared, with terrifying efficiency. The numbers defy comprehension. Temperatures exceeding 1 trillion degrees, kinetic energy propelling debris at 99% light speed, and radiation bursts bright enough to outshine entire galaxies for days. But raw power isn't the most staggering aspect, it's the transformation of energy forms. The glass shattering creates shock waves of acoustic energy, rippling through space as low-frequency gravitational vibrations. The plasma jets convert magnetic energy into particle acceleration, crafting beams that could strip atmospheres from planets light years away. Even the thermal energy radiating from the superheated debris disk carries enough punch to ionize interstellar clouds halfway across a galaxy. Unlike a supernova's brief flash, this event sustains its fury, with energy bleeding away across the electromagnetic spectrum for centuries as the neutron star slowly digests its meal. The implications ripple far beyond the collision site. That energy doesn't vanish, it seeds the cosmos. Gamma rays trigger nucleosynthesis in distant gas clouds, forging rare isotopes. Kinetic energy from ejected debris plows through molecular nurseries, compressing them into new star-forming regions. Even the gravitational waves carry energy across space-time, subtly heating the intergalactic medium as they dissipate. This single event could influence galactic chemistry for eons, altering the conditions for future planets and perhaps even life. Yet the true marvel lies in perspective. The universe routinely produces energies that humble human endeavors, but rarely in such a perfectly orchestrated cascade. Here, every joule tells a story, the tensile strength of glass surrendering to gravity, atomic bonds snapping under pressure, magnetic fields directing chaos into beams of lethal precision. It's a masterclass in physics' most extreme regimes, where energy ceases to be abstract and becomes the universe's most destructive and creative force. Under the neutron star's unimaginable gravity, the shattered remnants of the glass planet don't just melt or vaporize, they undergo a metamorphosis so extreme it rewrites the rules of matter itself. Picture a single shard of glass, once solid and transparent, now crushed under pressures billions of times greater than Earth's core. At these limits, the very structure of atoms collapses. Electrons, usually buzzing around their nuclei at a safe distance, are forced inward until they merge with protons, forming a sea of neutrons so dense it behaves like a single, gargantuan atomic nucleus. But even this neutron soup isn't the end of the story. Push further, and the neutrons themselves may break apart, their quarks and gluons, the fundamental building blocks of matter, spilling out to form a quark-gluon plasma, a state of matter so exotic it hasn't existed naturally since the first microseconds after the Big Bang. This plasma isn't like anything we encounter in daily life. It's a primordial soup where quarks, normally locked inside particles like protons and neutrons, roam freely, unshackled by the forces that usually bind them. In labs on Earth, scientists recreate this state for fractions of a second using particle colliders, but here, in the neutron star's grip, it forms on a planetary scale. The implications are staggering. Studying how glass, a material made of orderly silicon and oxygen, networks transforms into this chaotic quark soup could reveal secrets about how the universe itself condensed from a seething, formless energy into the structured cosmos we know today. But the surprises don't stop there. Some theories suggest that under these conditions, quarks might reorganize into strange matter, a hypothetical material where up and down quarks mix with their rarer cousin, the strange quark. Strange matter is thought to be ultrastable, possibly even more stable than the matter composing our everyday world. If true, the glass debris could, for a fleeting moment, become the universe's most indestructible substance before being swallowed by the neutron star's infinite hunger. The mere possibility opens doors to wild speculation. Could fragments of this strange matter survive the collision, drifting through space as bizarre, ultra-dense relics? Might they seed future cosmic events or even catalyze the transformation of other matter they encounter? The real treasure here isn't just the spectacle, it's the science. Every gram of glass-turned quark plasma is a time capsule, offering physicists a chance to test theories about the strong nuclear force, one of the least understood fundamental forces. How does matter behave when gravity overpowers even the mightiest atomic bonds? What happens when materials we consider solid are squeezed beyond their quantum limits? These aren't abstract questions, they're keys to understanding neutron stars themselves, the densest objects in the universe that aren't black holes. By simulating this process, researchers could inch closer to answering one of astrophysics' biggest mysteries: what lies at the heart of a neutron star? Is it truly a ball of pure neutrons, or does it harbor a core of free quarks, a cosmic secret waiting to be uncovered? This collision isn't just a disaster, it's a revelation. In the death throes of a glass planet, we catch a glimpse of the universe's most extreme alchemy, where ordinary matter is forged into forms that defy imagination. And in that transformation, we find not just destruction, but discovery, a reminder that the cosmos saves its most profound lessons for its most violent moments. Near the neutron star's crushing gravitational field, time itself warps in ways that defy everyday experience. Einstein's theory of relativity tells us that massive objects don't just bend space, they stretch time like taffy, creating bizarre distortions where clocks tick at wildly different rates depending on their location. For our ill-fated glass planet, this means the final moments of its destruction would appear radically different depending on where you're watching from. An observer far away in deep space would witness the entire catastrophe in extreme slow motion, as if watching a cosmic film stuck on half-speed. Picture this from the planet's perspective first. As tidal forces rip it apart, the process would feel brutally quick, perhaps mere minutes from first fracture to total disintegration. But from a safe distance, relativity's time-stretching effect would dramatically prolong the spectacle. What the glass world experiences as an hour of destruction might stretch into days or even weeks of slow, agonizing unraveling for outside viewers. The planet's shattering surface would crawl like molasses, each spire of glass toppling in dreamlike delay, while auroras from ionized particles would pulse languidly across its distorted shape. This time dilation isn't just a visual curiosity, it fundamentally changes how we'd study the event. X-ray telescopes would detect emissions fading far slower than physics predicts, their normally sharp spikes drawn out into eerie, extended waves. Gravitational wave detectors might catch the collision's chirp not as a quick burst, but as a prolonged, distorted note sliding down the scale. Even the neutron star's accretion disk, normally a whirlpool of frenetic activity, would appear to churn with surreal lethargy to distant eyes. The implications stretch beyond mere observation. This relativistic slow motion provides an unprecedented window into processes normally too swift to analyze. Normally, tidal disruption events flash by in hours here. Scientists could watch glass fracture dynamics in extreme detail, or track plasma turbulence patterns that usually blur into invisibility. It's nature's ultimate slow-motion camera, revealing physics hidden in the split-second chaos of cosmic violence. Yet the cruel irony is that while outside observers enjoy this extended view, the glass planet's hypothetical inhabitants, if any existed, would experience none of this grace period. To them, the end comes swiftly, their crystalline world crumbling in what feels like moments. This stark difference underscores relativity's most mind-bending lesson: there's no universal now. The universe doesn't agree on when events happen, only on the unbreakable laws that govern them. And in that dissonance between perspectives, we find one of astrophysics' greatest teachers, a reminder that reality itself is far stranger than our earth-bound intuition can grasp. The expanding debris cloud from the shattered glass planet doesn't just vanish into the void. It becomes a cosmic sculptor, reshaping the chemistry of everything in its path. Imagine a glittering storm of silica-rich fragments, some as fine as interstellar dust, others massive enough to qualify as rogue asteroids, all drifting outward at incredible speeds. This isn't just scattered wreckage, it's a delivery system for rare materials, carrying the ingredients of glass across light years. Over millennia, these particles will mix with molecular clouds, the same nurseries where stars and planets are born, infusing them with an abundance of silicon and oxygen, unlike anything found in typical star-forming regions. The implications for future worlds are profound. Planets forming in these enriched zones might develop crusts with unusual glassy layers, or atmospheres hazy with silica crystals. Asteroids could inherit a higher percentage of quartz-like minerals, turning them into cosmic mirrors that reflect starlight with eerie brilliance. Some fragments might even remain intact, wandering the galaxy as nomadic glass boulders, silent remnants of a world that once was. These travelers could one day collide with other planets, delivering their exotic cargo in fiery impacts. Picture a future Earth-like world pelted by glass meteorites, their transparent shards embedding in the soil like diamonds from the stars. But the debris cloud's influence isn't limited to solids. As the finer particles interact with radiation and stellar winds, they'll erode into molecules that can bond with hydrogen and other gases, forming compounds like silicon monoxide or silicates. These molecules could become the building blocks for entirely new kinds of cosmic chemistry, perhaps even complex silica-based structures that mimic the complexity of carbon-based organic molecules. In the coldest reaches of space, these silica-rich clouds might condense into strange, glassy ices, coating dust grains with shells as smooth as blown glass. The most fascinating twist, this process isn't hypothetical. We've already spotted silica-rich dust in planetary nebulae and supernova remnants, proof that violent cosmic events seed the galaxy with raw materials. The difference here is scale and purity. A glass planet's debris would be a concentrated injection of silica, a localized overdose that could skew the chemistry of an entire star-forming region for generations. Future astronomers studying young planets in these zones might notice anomalies, worlds with crusts too shiny, atmospheres too refractive, or rings that scatter light like prisms, all because a neutron star once devoured a world made of glass. This aftermath isn't just about destruction, it's a reminder that the universe recycles with ruthless efficiency. What was once a fragile, beautiful planet becomes a catalyst for new wonders, its fragments whispering to future worlds about the cataclysm that forged them. And in that transformation, we see the cosmos's grand paradox: to create, it must first destroy. The neutron star's feast comes at a cost. Its rigid outer crust, already under unimaginable strain, begins to crack under the pressure of new mass. These aren't ordinary quakes like the tremors that ripple through Earth's tectonic plates. A neutron star's crust is a lattice of atomic nuclei packed so tightly they form a crystalline shell harder than diamond, floating atop a quantum sea of free neutrons. When this hyperdense skin fractures, the resulting starquakes release more energy than our sun emits in centuries, all in milliseconds. The first tremors ripple outward as the star's rotation stutters, its perfect spin momentarily disrupted by crustal shifts deeper than planetary mountains. What follows is a fireworks show of high-energy radiation. As the crust fractures, pent-up magnetic energy bursts free, accelerating particles to near light speed. These quake-induced particle storms interact with the surrounding debris field in spectacular ways, supercharging already ionized glass plasma into even more exotic states. Some fragments caught in the magnetic shock waves are flash-heated until they emit X-rays like celestial strobe lights. Others are hurled outward with fresh violence, their trajectories suddenly altered by the star's convulsions. The most powerful quakes might even produce short gamma-ray bursts, focused beams of energy so intense they could be detected across intergalactic distances. But the real scientific treasure lies in the quake's seismic echoes. Just as earthquakes reveal Earth's inner structure, these cosmic tremors send vibrations through the neutron star's interior, offering hypothetical astronomers a sonogram of its hidden depths. The vibration's speed and dispersion could answer long-standing mysteries. How thick is the crust really? Does the core contain free quarks or other exotic particles? Each rupture acts like a hammer tap on a cosmic bell, its reverberations encoding secrets about matter at densities impossible to recreate on Earth. The influx of glassy debris adds another twist. Foreign material may temporarily weaken parts of the crust, creating fault lines where the star's own unimaginable gravity becomes its worst enemy. Imagine a pane of glass with one tiny scratch. Now place it under hydraulic press capable of exerting billions of tons of pressure. That's the neutron star's dilemma, its perfect crystalline crust now adulterated by silica-rich contaminants, creating vulnerabilities where none existed before. The resulting quake patterns might appear erratic compared to a pure neutron star's more predictable ruptures, like a skater stumbling after stepping on uneven ice. This seismic pandemonium leaves lasting marks on the system. Some ejected debris receives an extra velocity kick from quake-powered magnetic slingshots, escaping the neutron star's grasp entirely. The accretion disk wobbles as seismic shocks ripple through it, its inner edge flaring unpredictably like a candle in a draft. Even the star's spin, normally regulated with atomic clock precision, becomes erratic, its rotation rate jittering like a malfunctioning turbine. For observers, these effects transform what might have been a clean tidal disruption event into a messy, multivariable puzzle, one where every new X-ray flare or gamma-ray spike could trace back to either the planet's destruction or the star's internal upheavals. Yet amid this chaos there's profound beauty. The same forces that shattered a world now make the neutron star itself briefly unstable, revealing its inner workings through violent self-exposure. It's a reminder that even the cosmos's most perfect objects, spheres so precise they rival atomic clocks in their rotational regularity, have breaking points. And when they crack, they don't fail quietly. They broadcast their distress across the universe in a language of light and gravity waves, waiting for someone to decipher their cries. The neutron star's feast has a tipping point, a moment where even its unimaginable density can no longer resist gravity's ultimate victory. Every shard of glass it consumes adds weight, pushing the star closer to a cosmic cliff's edge. Neutron degeneracy pressure, the quantum force that keeps these stellar remnants from collapsing further, fights valiantly against the mounting mass. But physics has limits. Cross the threshold somewhere around 2 to 3 times the sun's mass, and that delicate balance shatters. The star's core implodes in a fraction of a second, its structure vanishing beneath what astronomers call the event horizon, the point of no return where even light cannot escape. This transformation would be both sudden and silent from an outsider's perspective. One moment, the system blazes with X-rays and gamma rays as glass plasma spirals into the neutron star's grasp. The next, an eerie quiet. The accretion disk's fiery glow winks out mid-rotation like a cosmic power failure. Gravitational waves from the final collapse might ripple outward, but the electromagnetic fireworks cease abruptly as if a curtain drops on the universe's most violent stage. The debris field, moments ago a luminous whirlpool, now orbits nothing visible, just an inky darkness where the star once stood. Yet the real drama happens invisibly. As the neutron star's core collapses, its matter undergoes one last metamorphosis. Protons and electrons, already crushed into neutrons, may dissolve further into a soup of quarks, or perhaps something even stranger, like a Bose-Einstein condensate of exotic particles theorists have yet to name. The new black hole's birth erases this information from the observable universe, leaving behind only three telltale properties: mass, spin, and electric charge. Everything else, the star's magnetic field, its crustal imperfections, even the chemical fingerprints of the glass it consumed, is lost to what physicists call the no-hair theorem, a poetic way of saying black holes are the universe's simplest objects despite their complexity. For the surrounding debris, the transition brings chaos. Orbits that were once stable around a neutron star's precise gravity now spiral unpredictably in the black hole's warped spacetime. Some fragments might gain enough velocity to escape entirely, slingshotting into interstellar space like glass shrapnel. Others will continue their death spiral, but with a key difference. Instead of glowing hot as they rub against other debris, they simply vanish into the darkness, their light red shifting into imperceptibility as they cross the event horizon. The black hole's shadow would grow slowly as it consumes the remnants, a silent predator claiming its meal. This moment holds profound implications for astrophysics. The exact mass limit for neutron stars, the dividing line between stellar remnant and black hole, remains one of the field's holy grails. Witnessing this transition in real time, even hypothetically, offers clues about the equation of state for ultra-dense matter, basically, how particles behave when squeezed beyond all reason. The sudden cutoff of emissions would also provide a clean laboratory for studying how accretion disks behave when their central engine disappears, a scenario that might explain some of the universe's more mysterious flickering lights. Most hauntingly, the glass planet's demise would leave no visible trace in the black hole's final state. All that beauty, the prismatic shards, the auroras, the swirling plasma, ends up compressed into a singularity smaller than an atom. The universe forgets the details, remembering only the total mass added. It's a humbling reminder that for all their violence, black holes are the cosmos' ultimate simplifiers, reducing complexity to pure gravity. And in that simplification, they hide some of nature's deepest secrets, secrets that, for now, remain locked behind an event horizon we cannot pierce. Consider the cosmic odds stacked against this encounter. A neutron star, one of the rarest objects in the galaxy, crossing paths with a planet made entirely of glass, a material that requires such precise conditions to form on a planetary scale that its existence borders on fantasy. The universe is overwhelmingly vast, yet filled with emptiness, so much so that even in a galaxy with hundreds of billions of stars, the average distance between them is so immense that direct collisions are almost unthinkable. For these two specific objects to meet, countless variables must align perfectly. The glass planet must form in a system rich in silicon and oxygen, avoid destruction for billions of years, and then drift into the gravitational crosshairs of a wandering neutron star. The rarity goes beyond mere statistics. Neutron stars themselves are relics of extreme violence. Only the most massive stars, a fraction of 1% of all those born, explode in supernovas dense enough to leave these ultra-compact remnants behind. Even then, most neutron stars roam the galaxy alone, their paths untethered from other celestial bodies. Meanwhile, glass planets, if they exist at all, would be fragile anomalies, their brittle structures vulnerable to everything from asteroid impacts to the gentle nudge of a passing star's gravity. For these two rarities to collide isn't just unlikely, it's like two needles finding each other in a cosmic haystack the size of 1,000,000 solar systems. Yet it's this very improbability that makes the scenario so valuable to science. Extreme events, no matter how rare, test the boundaries of our understanding. The 2017 detection of two neutron stars colliding, a phenomenon once thought to occur once every 100,000 years per galaxy, rewrote textbooks on gravitational waves and heavy element formation. Similarly, contemplating a glass planet's demise forces us to stretch our models of material science, plasma physics, and orbital dynamics beyond their usual limits. Sometimes it's the universe's most unlikely encounters that teach us the most about its fundamental rules. There's also a philosophical dimension to this rarity. In a cosmos where most matter is hydrogen and helium, where rocky planets outnumber glass ones by unimaginable margins, such an event becomes a reminder of how diverse the universe's creativity can be. It challenges us to wonder, if something this specific could happen, what other impossible-seeming phenomena might lurk in the depths of space, waiting for the right set of circumstances to reveal themselves. The collision may be a 1 in a quintillion occurrence, but in an infinite universe, even the rarest events must happen somewhere, if only we're patient enough to look. The destruction of a glass planet by a neutron star isn't just a spectacle, it's a mirror held up to our own existence. For all its beauty, the universe operates on a timescale where permanence is an illusion. Planets, stars, even galaxies are temporary structures in a cosmic dance of creation and annihilation. Earth, with its oceans and continents, feels solid and eternal to us, but on a geological, let alone astronomical timeline, it's just as fragile as that shattered glass world. The same forces that tear apart stars and reshape nebulae are always at work, even if their effects unfold too slowly for human eyes to see. This collision forces us to grapple with a humbling truth: stability is relative. Earth's position in the Goldilocks zone, its magnetic shield, its tectonic recycling, all these delicate balances could be overturned by a single cosmic event. A nearby supernova, a rogue black hole, or even a subtle shift in the sun's behavior could rewrite our planet's future in an instant. The glass planet's demise is a reminder that the universe doesn't guarantee safety, only opportunity. For billions of years, conditions aligned perfectly for life to emerge here, but those conditions are fleeting on a cosmic clock. Yet there's an unexpected comfort in this impermanence. The same forces that destroy also create. The silicon and oxygen atoms from that shattered glass world will one day be recycled into new planets, new stars, perhaps even new life. Our own bodies are made of stardust from long-dead suns, a proof that endings are also beginnings in disguise. The neutron star's violence isn't mindless destruction, it's transformation in its most raw and elemental form. This duality, beauty and brutality intertwined, is woven into the fabric of reality. Supernova scatter the heavy elements needed for life even as they obliterate worlds. Black holes shred stars but also power quasars whose light illuminates the early universe. The glass planet's destruction, for all its violence, might seed future cosmic wonders we can't yet imagine. Perhaps that's the ultimate lesson. The universe's indifference isn't cruelty, it's the price of possibility. Without these cataclysms, the ingredients for planets like ours would still be locked inside ancient stars. The same forces that could one day end Earth are the ones that made it possible in the first place. In that paradox, we find a strange kind of kinship with that shattered glass world. Its story, like ours, is just a fleeting chapter in a much grander tale, one where destruction and creation are two sides of the same coin, spinning endlessly in the void. The next generation of telescopes will turn the universe's most violent encounters into observable spectacles. Imagine the James Webb Space Telescope, with its infrared eyes peeled for the faint glow of vaporized glass, capturing spectral lines that scream silicon and oxygen in wavelengths we've never seen before. Or picture LISA, the upcoming gravitational wave observatory, drifting in space with lasers so precise they can detect the subtlest ripples from a cataclysm a billion light-years away. These instruments won't just watch the cosmos, they'll eavesdrop on its most extreme physics experiments, turning hypotheticals like our glass-planet collision into detectable, measurable events. What makes these tools revolutionary isn't just their sensitivity, it's their teamwork. Webb might spot the infrared afterglow of shattered silica, while LISA records the gravitational thud of debris spiraling into a neutron star. Combined, their data could reconstruct the entire catastrophe like cosmic forensic scientists. Unusual spectral signatures, say, a spike at 4.7 micrometers, where silicon dioxide vapor glows brightest, would stand out like neon signs in the dark. Even the absence of expected elements, like the telltale gold and platinum from neutron star mergers, could hint at something stranger, a planet made not of metal but of glass. The real game-changer, time-domain astronomy. Projects like the Vera Rubin Observatory will scan the entire visible sky every few nights, catching transient events that earlier surveys would have missed. A glass planet's destruction might flare brightly for mere hours before fading a blink in cosmic terms, but now within our grasp to capture. Automated systems will flag anomalies in real time, triggering follow-ups from other telescopes to dissect the event across the electromagnetic spectrum. But the Holy Grail would be catching such a collision in its earliest stages. Future neutrino detectors, sensitive to the torrent of ghostly particles released as the neutron star's tidal forces first flex the glass planet, might give us a heads-up before the light show begins. It's like having a front-row seat to the universe's most exclusive demolition derby, with every instrument tuned to a different facet of the chaos. This isn't just about confirming a thought experiment, it's about expanding our cosmic vocabulary. Each new observatory adds syllables to the language we use to decode the universe. When we finally spot a neutron star shredding an exotic world, whether glass or diamond or ice, it won't just validate decades of theory. It'll remind us that the cosmos is always stranger than we dare hypothesize, and that somewhere in the data streams of tomorrow's telescopes, the next paradigm-shifting discovery is already waiting. The collision between a glass planet and a neutron star isn't just a scientific curiosity, it's a canvas waiting for artists to bring its surreal violence to life. Throughout history, creators have turned to the cosmos for inspiration, from Vincent van Gogh's swirling starry nights to Stanley Kubrick's hypnotic Stargate sequence. But this scenario offers something uniquely mesmerizing, a cataclysm where destruction becomes art. Picture a filmmaker capturing the moment the planet's surface erupts into glittering shards, each fragment refracting the neutron star's eerie glow into fractured rainbows. Or a digital painter rendering the plasma jets as luminous brushstrokes against the void, their colors shifting from violet to X-ray white as they pierce interstellar dust. The very physics that make this event so extreme, time dilation, relativistic effects, quantum material transformations, could birth entirely new visual languages for cosmic storytelling. Science fiction has flirted with similar concepts before. Remember the diamond planet in Doctor Who or the crystalline entities from Star Trek? Those were mere glimpses compared to what this collision offers. A glass world shattering in slow motion under tidal forces could become the next iconic sci-fi tableau, joining the likes of black holes and supernova in popular imagination. Composers might score the event with glass harmonicas and other crystalline instruments, their resonant tones mirroring the planet's fragility. Game designers could build entire mechanics around the debris field's physics, where players navigate relativistic shard storms or harness the neutron star's magnetic fury. Even fashion designers might draw from the collision's palette metallic blues from the plasma jets, prismatic reflections from the glass dust, the Inkai blacks of warped spacetime. But the real power of these artistic interpretations lies in their ability to bridge the gap between abstract astrophysics and human emotion. Equations can describe the tidal forces tearing the planet apart, but a sculptor working with fused silica and LED lighting could make audiences feel that destruction in their bones. A poet might juxtapose the neutron star's relentless hunger with the glass planet's fleeting beauty, turning cosmic violence into a meditation on impermanence. These creations wouldn't just illustrate science, they'd expand its reach, inviting viewers to engage with astrophysics through wonder rather than formulas. The collision also challenges artists to invent beyond earthly reference points. How do you depict light bending through a planet-sized lens? What sound does a continent-sized sheet of glass make when it fractures in vacuum? These questions push creative boundaries as fiercely as the event itself pushes physical ones. Some might take literal approaches, using supercomputer simulations as storyboards. Others could lean into abstraction, letting the neutron star's distortions warp their medium sculptures that melt under polarized light, or films where the frame rate slows to mirror relativistic time dilation. Perhaps most exciting is how these works could feed back into science communication. The same visualizations that dazzle gallery crowds might later appear in lecture halls, helping professors explain tidal disruption events to students. A viral animation of the glass planet's demise could spark more public interest in neutron stars than any journal article. This symbiosis between art and science isn't new. Da Vinci blended them seamlessly, but in an era of VR and AI tools, the potential for collaboration is greater than ever. The artists who dare to tackle this scenario won't just be interpreting the cosmos, they'll be helping redefine how humanity sees its place within it. What emerges isn't merely entertainment or education, but a new cultural touchstone, a shared visual language for cosmic violence that resonates across disciplines. Just as Picasso's Guernica channeled the horrors of war into enduring art, these creations could crystallize the universe's most extreme physics into something profoundly human. The neutron star's destruction of a glass planet may last mere hours in reality, but through art, its echoes could inspire for centuries. Hypothetical collisions like this aren't just cosmic daydreams, they're vital teaching tools that crack open the door to extreme astrophysics. Picture a classroom where students grapple with abstract concepts like tidal forces and quantum degeneracy pressure. Now give them a scenario where a neutron star literally stretches a planet like taffy before shattering it into glittering debris. Suddenly, those textbook equations transform into a visceral, unforgettable spectacle. This mental imagery does more than captivate, it builds intuition. When learners visualize glass spires crumbling under gravitational stress, they internalize how matter behaves at limits far beyond earthly experience. The educational power lies in the collision's layered complexity. It's not one lesson but dozens woven together. Planetary science comes alive as students contrast glass formation with Earth's rocky geology. Material physics gains new relevance when analyzing how silica fractures differently under neutron star gravity versus a lab bench. Even chemistry enters the mix, with vaporized glass atoms emitting telltale spectral lines that future astronomers might detect. Each discipline finds a foothold in this catastrophe, turning it into a multidisciplinary playground for curious minds. these thought experiments also reveal how astrophysicists work. Real researchers routinely use extreme scenarios to stress test theories, just as engineers simulate 100-car pileups to improve vehicle safety. Scientists imagine collisions like this to probe the boundaries of known physics. When students engage in similar exercises, they're not just memorizing facts, they're learning the scientific method at its most creative. How do you model plasma turbulence in an accretion disk? What equations predict when a neutron star's crust will quake? These become tangible problems rather than abstract homework. Perhaps most crucially, such scenarios cultivate cosmic perspective. A glass planet's destruction underscores how planetary diversity likely exceeds our wildest imagination. If hypothetical worlds can be made of diamond, metallic hydrogen, or, in this case, pristine silica, what other exotic configurations might exist? This realization sparks deeper questions about planetary formation. Could glass planets form around silicon-rich stars? Might we find fragments of such worlds in meteorite samples? Suddenly, our solar system feels like one possibility among infinite others. The neutron star's role in this drama offers equally rich lessons. These remnants exemplify nature's ability to compress entire stars into city-sized orbs without breaking the laws of physics. Students often struggle with scales. How can something so small weigh more than the sun? Visualizing a teaspoon of neutron star material outweighing Mount Everest makes quantum degeneracy pressure feel concrete rather than mystical. The star's magnetic fields, spin rates, and ultimate fate as a potential black hole candidate become accessible through this narrative lens. Beyond classrooms, these exercises sharpen professional research skills. Modern astronomy increasingly relies on simulations to interpret telescope data. By wrestling with hypotheticals, students build mental frameworks for when real cosmic oddities appear. That bizarre infrared glow from a distant star, could it be vaporized glass from a recent collision? That unusual gravitational wave signal, might it match a neutron star consuming an exotic world? Training minds to ask these questions prepares the next generation of astronomers for discoveries we can't yet anticipate. At its core, this thought experiment embodies science's greatest gift, the ability to explore the impossible to better understand the real. Whether glass planets exist matters less than what imagining them teaches us about neutron stars, planetary limits, and the universe's boundless creativity. In the end, that's the true value of stretching physics to its breaking point, not to predict what's out there, but to equip ourselves with the wonder and tools to find out. The silence after the cataclysm is not empty, it hums with the quiet aftermath of cosmic violence. Where a glass planet once orbited, only faint echoes remain, an expanding debris field glowing with residual heat, its silica-rich particles scattering starlight like interstellar dust motes. The neutron star, or the black hole it may have become, now sits motionless at the center of this graveyard, its gravitational pull too weak to reclaim the outermost fragments drifting beyond its grasp. These remnants don't rush outward in a uniform cloud, they move with a strange, ethereal hierarchy. The smallest particles, light as photons but rich with silicon and oxygen, are pushed fastest by radiation pressure, forming a hazy halo that could span solar systems. Larger chunks, some the size of mountains, still glinting with smooth, fracture-polished surfaces, lag behind, tracing slow, lonely arcs through the void. But this debris field is more than rubble, it's a time capsule. Each shard carries a record of the destruction encoded in its structure. Microscopic stress lines reveal how the tidal forces tore the planet apart. Bubbles trapped inside some fragments hold traces of vaporized atmosphere or volatile compounds that once flowed beneath the glass crust. and the very distribution of the debris tells a story. Denser clusters mark where the planet's internal structure held firm longest, while sparse zones hint at regions that shattered like sugar glass at the neutron star's first gravitational touch. Future civilizations, or our own far-flung probes, might one day analyze these fragments and reconstruct the planet's composition down to the atomic level, piecing together a world lost to time. The neutron star itself enters a new phase of existence. If it survived the collision intact, its surface might now be littered with exotic glass-ceramic hybrids, materials forged in the accretion disk's inferno and later deposited like cosmic snowfall. These aren't ordinary silicates, they're neutron-irradiated compounds with crystalline structures warped by the star's gravity, some potentially denser than diamond. Their presence could subtly alter how the star cools or how its magnetic field interacts with the surrounding vacuum. If the star collapsed into a black hole, the debris field's behavior becomes even stranger. Without a central light source to illuminate them, the fragments fade into invisibility, but their gravitational influence remains. Astronomers might detect their presence through microlensing events, as drifting glass shards bend the light of background stars like phantom lenses. Yet the most haunting transformation is in the light itself. During the collision's peak, the system blazed across the electromagnetic spectrum. Now, only faint signatures linger, infrared whispers from cooling glass dust, occasional radio crackles as charged particles spiral in weak magnetic fields. Over centuries, even these will fade. The debris will disperse further, some grains eventually joining interstellar clouds, others perhaps colliding with random asteroids and leaving behind microscopic craters lined with fused silica. The neutron star or black hole will continue its lonely journey, bearing no visible trace of the planet it consumed save perhaps for a subtle enrichment of heavy elements in its stellar neighborhood, a cryptic clue for future astrochemists to decipher. This silence isn't an ending, it's a transition. The glass planet's remnants will endure longer than most civilizations, drifting until gravitational nudges from passing stars or molecular clouds scatter them across the galaxy. A few might even become time travelers of a sort, grains propelled to relativistic speeds by the collision's violence, crossing interstellar space for eons before perhaps, just perhaps, embedding themselves in the fledgling crust of a newborn world billions of years hence. There, under alien skies, they might finally rest, their crystalline lattices still whispering of the day they were torn from a world made of glass. For all the vivid detail we've painted about this cosmic collision, the truth is, we're still standing at the edge of a vast unknown. The existence of glass planets hangs in a tantalizing gray zone between theoretical possibility and observational reality. While we've found worlds of diamond-like carbon and lava-covered super-Earths, a planet with a structure as uniform and fragile as glass remains undiscovered. The challenge isn't just finding one, it's understanding how such a delicate object could survive the chaos of planetary formation in the first place. Picture a protoplanetary disk rich in silica, where temperatures and pressures align just right for molten glass to cool into a cohesive sphere rather than shattering into countless fragments. The odds seem vanishingly slim, yet the universe has a habit of defying expectations. Dive deeper, and the mysteries multiply. How would a glass planet's interior behave without the layered differentiation we see in rocky worlds? Earth's molten core and shifting tectonic plates rely on density variations, heavy metals sinking, lighter minerals rising. But a planet made predominantly of silica might lack those dynamics, potentially forming a more homogeneous structure with minimal internal movement. Could it still generate a magnetic field without convective currents, or would it be defenseless against solar radiation, its surface scoured by stellar winds over eons? These aren't just academic puzzles, they're keys to understanding how exotic materials reshape planetary evolution. Then there's the question of time. Glass, for all its beauty, is inherently unstable on geological timescales. Over millions of years, even the hardest volcanic obsidian begins to flow and to form under its own weight. Scale that up to a planet, and the implications are staggering. Would a glass world slowly slump into a sphere under relentless gravity, its surface smoothing like aging window panes? Or might it develop internal fractures from tidal stresses, creating vast subglacial oceans of superheated silica, a labyrinth of liquid glass rivers beneath a brittle crust? The answers could rewrite our definitions of planetary habitability, suggesting landscapes where chemistry plays out in ways no Earth-bound geologist could anticipate. The neutron star's role in this thought experiment raises equally provocative questions. If such a collision occurred, would the remnants carry detectable traces of the planet's original structure? Simulations suggest neutron stars can, remember, accreted material through subtle changes in their crust composition. But could a pulse of vaporized glass leave a measurable imprint? And what of the debris? Might some fraction of it escape with minimal alteration, preserving microscopic records of the planet's pre-collision state? Future missions analyzing interstellar dust for unusual isotopic ratios could one day stumble upon these cosmic breadcrumbs. Perhaps the most compelling unknown is whether we're asking the right questions at all. Our models assume glass planets would resemble giant versions of terrestrial silica, but what if their formation pathways create entirely novel materials? Under extreme pressures, silica can morph into stishovite, a mineral denser than quartz found in meteorite impact sites. Could a planet-scale version exhibit properties blending crystalline and glassy behaviors, defying conventional classification? The universe has already shown us matter can exist in states beyond solid, liquid, and gas, from neutron star material to quark-gluon plasma. A true glass planet might challenge our very vocabulary for describing worlds. These gaps in knowledge aren't shortcomings, they're invitations. Every unresolved question about glass planets and their violent ends illuminates how much we still have to learn about planetary diversity. They push astronomers to refine their instruments, theorists to stretch their models, and perhaps most importantly, they remind us that the cosmos reserves its greatest wonders for those willing to confront the limits of the known. The next breakthrough might come from a telescope's unanticipated data spike, a supercomputer's aberrant simulation result, or even our artists rendering that sparks a scientist's epiphany. In the end, the value of these mysteries isn't just in their solutions, but in how the pursuit reshapes our vision of what's possible. A neutron star devouring a rocky planet would be a brutal, grinding affair like a sledgehammer pulverizing a mountain. The dense metals and silicates in a world like Earth resist shattering, instead deforming under the star's gravity like putty before erupting into molten geysers. The debris field would be thick with vaporized metals, iron, nickel, and heavier elements churned into a superheated plasma soup. Energy release would skew toward X-rays and gamma rays as atomic nuclei are stripped bare, their electrons torn away in the magnetic maelstrom. Compare that to an icy planet's demise, a far messier explosion of volatile compounds. Methane, ammonia, and water ice wouldn't just melt, they'd flash boil into steam, then dissociate into hydrogen and oxygen under the intense radiation, creating a transient atmosphere around the neutron star before being ripped apart. The light show would lean toward ultraviolet and radio wavelengths, with icy fragments evaporating like comets on steroids. But a glass planet, its destruction is a spectacle of refraction and fragmentation. Unlike rock, which deforms, or ice, which vaporizes, glass behaves unpredictably under extreme stress. it fractures along microscopic flaws, shattering into cleaner, sharper fragments than any other material. This means the debris field would glitter with prismatic shards, some large enough to reflect the neutron star's light like celestial disco balls, others so fine they'd scatter starlight into ethereal halos. The energy release would be a kaleidoscope, visible light from refracted beams, infrared from cooling silica dust, and X-rays where plasma jets punch through the glittering wreckage. Material composition also dictates the aftermath. A rocky planet's remains would leave the neutron star dusted in heavy elements, subtly altering its crust's conductivity. Icy debris might temporarily quench the star's magnetic field, as volatile molecules interact with charged particles in ways we don't fully understand. But glass, its high silica content could form bizarre, transient minerals in the accretion disk silicon oxides with structures warped by the star's gravity into configurations no lab could replicate. These exotic byproducts might linger just long enough to emit unique spectral signatures before dissolving into the neutron soup. The key difference lies in fragility. Rock resists, ice explodes, but glass dances with destruction, its very brittleness creating a debris field unlike anything else in the cosmos. Where a rocky collision leaves behind a smoldering haze and an icy encounter a dissipating cloud, a glass planet's demise etches its story in light, its fragments acting as billions of tiny lenses bending the universe's glow into a farewell masterpiece. From Earth, the collision would appear as a brilliant but harmless spark in the night sky, a new star flaring to life before fading over weeks or months. To the naked eye, it might resemble a supernova, though with a peculiar blue-white hue from all that refracted silica. Amateur astronomers would train their telescopes on the glowing debris field, marveling at how the neutron star's gravity bends the light into intricate Einstein rings. Scientists would scramble to analyze the event's light curve, comparing it to models of tidal disruption. For most of humanity, it would be a dazzling cosmic curiosity, a trending topic for a few news cycles before fading into astronomical archives. But shift the scenario slightly, bring that collision within a few hundred light-years of Earth, and the story changes dramatically. The same spectacle that delighted distant observers becomes an existential threat. Gamma-ray bursts from the jets, though narrow, could strike our planet with the energy of 1,000 solar flares if we're unlucky enough to be in their path. The initial flash would ionize our upper atmosphere within seconds, disrupting global communications and frying satellites. Auroras would erupt at the equator as charged particles bombard the magnetosphere, while the ozone layer takes years to recover from the radiation beating. Even without a direct gamma-ray hit, the lingering X-rays and cosmic rays from the expanding debris could increase cancer risks worldwide for decades. The gravitational waves from such a nearby event would be subtle but measurable, not enough to shake the planet, but sufficient to perturb sensitive instruments. LIGO detectors might ring like cosmic tuning forks, recording oscillations in spacetime itself. More unsettling would be the potential for gravity echoes, secondary ripples caused by debris falling into the neutron star long after the initial collision. These delayed signals could arrive without warning, a reminder that in relativity, cause and effect don't always follow intuitive timelines. What makes this hypothetical so chilling is how little warning we'd have. Light and gravity waves travel at the same speed we'd see the first flare simultaneous with feeling its gravitational fingerprint. There would be no preparation, only reaction. Our planet has survived similar astrophysical violence before evidence suggests gamma-ray bursts may have triggered mass extinctions in Earth's deep past. But modern civilization, with its reliance on delicate electronics and orbital infrastructure, is uniquely vulnerable to such cosmic tantrums, yet paradoxically, this vulnerability underscores our growing cosmic awareness. Ancient humans might have interpreted the sudden apparition as an omen or deity. Today, we'd understand it as physics in its purest, most unforgiving form, a reminder that the universe operates on scales that dwarf human concerns. The same telescopes that would document the event's aftermath are also our early warning system, scanning the heavens for potential threats. That we can even contemplate such scenarios, let alone model their consequences, marks a profound shift in our relationship with the cosmos. We've gone from passive observers to active participants in decoding universal violence, armed with mathematics instead of mythology. Perhaps the greatest lesson lies in perspective. A collision that obliterates a world becomes, at sufficient distance, merely a data point in an astronomer's catalogue. The universe balances creation and destruction on scales we're only beginning to comprehend, where one civilization's apocalypse is another's light show. This duality forces us to confront uncomfortable truths about our place in the cosmic order, simultaneously insignificant against the backdrop of stellar catastrophes, yet rare and precious in our ability to witness them. The glass planet's demise, whether distant threat or celestial fireworks, becomes a mirror reflecting both the fragility of our existence and the resilience of our curiosity. What seems like pure imagination, a glass planet shredded by a neutron star, holds real value as a scientific stress test. These extreme hypotheticals act like cosmic crash dummies, helping researchers probe the limits of known physics. When theorists simulate such an unlikely collision, they're not just indulging in fantasy, they're pressure-testing equations against scenarios where textbook assumptions break down. Take tidal disruption models, for instance. Normally, these calculations assume rocky or gaseous worlds, but introducing a brittle, uniform material like glass forces entirely new variables into play. How do stress fractures propagate in a planet-sized crystal? Can silica vaporize before melting under neutron star gravity? Each question exposes gaps in our understanding, pushing scientists to refine their simulations with finer detail. History shows how useful these thought experiments can be. Decades before we detected gravitational waves, Einstein used extreme scenarios involving falling elevators and light beams to explore relativity's implications. Similarly, pondering a glass planet's destruction might reveal overlooked behaviors in high-energy plasmas or quantum materials. Some of the most groundbreaking discoveries, from black holes to quantum entanglement, emerged from scientists first wrestling with what-if scenarios that seemed absurd at the time. The glass planet collision joins this tradition, serving as a sandbox where physicists can tweak variables like material composition, spin rates, or magnetic field strengths to see how the universe might respond under conditions no lab can replicate. Beyond theory, this scenario inspires tangible innovations in observation. If telescopes someday spot an unexplained infrared glow near a neutron star, could it be vaporized silica from a devoured world? The hypothetical spectral signatures explored here become a reference library for future anomalies. Instruments like the James Webb Space Telescope now have potential fingerprints to look for specific wavelengths where shattered glass might whisper its presence across the cosmos. Even gravitational wave detectors benefit, as models of asymmetric tidal disruptions could help interpret unusual chirps in their data. The most profound impact might be cultural. By stretching our imaginations to contemplate such rarities, we cultivate a mindset that expects cosmic diversity. If a planet can be made of glass, what other impossibilities might await discovery? This intellectual flexibility has practical value. It prepares scientists to recognize and interpret truly alien phenomena when they inevitably appear in the data. After all, pulsars were dismissed as LGM signals, little green men, when first detected, their regularity seeming too artificial to be natural. Today, we know them as neutron stars. Tomorrow's enigma, perhaps a glass world's remnants, will demand the same openness to rewriting expectations. Ultimately, these exercises remind us that the universe's creativity dwarfs our own. For every rule we've deduced about planetary formation or stellar evolution, exceptions lurk in the shadows. By daring to model the improbable, we don't just prepare for surprises, we honor science's essential spirit, the courage to ask, to wonder, and to follow the evidence wherever it leads, even into the heart of a neutron star's fury. There's a haunting elegance to the way the universe destroys a paradox where annihilation becomes art. Picture the moment the glass planet fractures, vast, translucent shards spinning away from the rupture, each one catching the neutron star's glare and splintering it into 1,000 prismatic arcs. The debris doesn't just scatter, it dances, arranging itself into transient constellations that glow with refracted light, as if the cosmos itself is composing a symphony of shattered crystal. This isn't chaos, it's a brutal kind of choreography where gravity and momentum conspire to turn demolition into something mesmerizing. The plasma swirling into the neutron star's grasp adds another layer to this cosmic canvas. Superheated to millions of degrees, the vaporized glass emits light across the spectrum: ultraviolet ribbons, X-ray flashes, and eerie infrared halos from cooling dust. These aren't random bursts, they pulse in rhythm with the star's rotation, like a lighthouse beam cutting through a storm of diamonds. The accretion disk forms a luminous whirlpool, its inner edges warped by relativistic effects into a glowing ring that seems to defy physics. To a distant observer, the entire scene might resemble a celestial Van Gogh painting, with swirling blues and golds layered over the void's blackness. Even the violence of gravitational waves contributes to the spectacle. As space-time ripples outward from the collision, it subtly distorts the light traveling through it, creating fleeting lensing effects that magnify and twist the debris field's glow. Background stars briefly stretch into smears of light, as if the universe is peering through a funhouse mirror. These distortions are invisible to the naked eye, but to instruments like LIGO, they are part of the event's signature, a silent vibration that sings of the planet's demise in a frequency only mathematics can translate. What makes this beauty so unsettling is its impermanence. The dazzling debris field will disperse, the plasma jets will fade, and the neutron star, now heavier, perhaps slower, will resume its lonely journey. The entire masterpiece might last only weeks before the universe reclaims its materials, recycling them into new stars, new planets, new possibilities. That transience is the heart of the paradox, destruction so breathtaking it rivals the birth of nebulae or the glow of newborn stars. It's a reminder that creation and annihilation aren't opposites, they're partners in an endless cycle, each feeding the other in ways we're only beginning to comprehend. Perhaps the most profound lesson lies in perspective. From a human scale, the collision is unthinkable violence, a world obliterated in hours. But from the universe's vantage, it's just another transformation, no different from a glacier carving valleys or a supernova seeding space with stardust. The beauty isn't in the destruction itself, but in the forces laid bare: gravity's mastery, light's resilience, matter's endless adaptability. For a brief moment, the curtain pulls back, and we see the machinery of the cosmos at work, forging wonder from wreckage. And in that glimpse, we find a strange comfort. Even in its most violent acts, the universe never wastes, it reimagines. While we may never witness the cataclysmic dance between a neutron star and a glass planet, the mere act of imagining such an encounter rewires how we see the cosmos. It's easy to think of space as a static gallery of familiar objects, gas giants, rocky worlds, twinkling stars. But scenarios like this shatter that illusion. The universe operates on a scale where the ordinary becomes extraordinary, where materials we consider fragile on Earth can form entire planets, and where stellar remnants wield gravity like cosmic sculptors. This thought experiment isn't just about destruction. It's a celebration of the universe's boundless creativity, a reminder that the rules of physics can craft wonders far stranger than fiction. Consider how this hypothetical collision mirrors real astronomical discoveries. Just a few decades ago, planets outside our solar system were purely theoretical. Now we know of worlds with diamond rain, molten iron skies, and oceans hidden beneath icy crusts. Each new find pushes the boundaries of what we deem possible, proving that the cosmos thrives on variety. A glass planet might seem implausible today, but so did rogue planets drifting between stars or pulsars, spinning faster than kitchen blenders until we found them. The universe doesn't just tolerate outliers, it revels in them, using the same fundamental forces to build both the mundane and the miraculous. This exercise also sharpens our scientific curiosity. By asking, what if, we uncover gaps in our understanding. How would silica behave under neutron star-level gravity? Could a magnetic field trillions of times stronger than Earth's alter the way glass fractures? These questions aren't frivolous, they pressure test our models, revealing where our knowledge ends and discovery begins. When researchers simulate extreme events, they're not just playing with equations, they're preparing for the day a telescope captures something truly inexplicable. After all, the most groundbreaking discoveries often begin as "that's impossible" moments. On a deeper level, this scenario humbles us. A glass planet's destruction is a fleeting event in cosmic terms, but its implications ripple across time and space. The same forces that annihilate worlds also seed future ones, scattering raw materials for new stars, planets, and perhaps even life. It's a poignant reminder that we're part of this cycle. Our atoms, too, were forged in stellar furnaces and violent collisions. The universe doesn't distinguish between creation and destruction. It sees only transformation, an endless reimagining of matter and energy. So while we may never find a neutron star locked in a deadly embrace with a crystalline world, the value lies in the journey of imagination itself. These mental voyages stretch our perception of reality, training us to recognize the extraordinary hiding in plain sight. Whether it's the delicate balance keeping Earth habitable or the violent beauty of a supernova, the cosmos thrives on contrasts, fragility and strength, chaos and order, endings and beginnings. And in that tension, we find not just answers, but better questions to guide our next exploration into the unknown. From the first shudder of tidal forces to the glittering aftermath, the destruction of a glass planet by a neutron star reveals the universe's capacity for both violence and beauty. We've witnessed how gravity bends and fractures an entire world, how matter transforms under impossible pressures, and how the cosmos recycles catastrophe into new possibilities. This collision, though hypothetical, is more than just a spectacle. It's a laboratory for extremes, testing the boundaries of what we know about materials, gravity, and the life cycles of planets. What makes this scenario so compelling isn't just the physics, it's the questions it leaves unanswered. Could a glass planet truly form, or would its fragility doom it before a neutron star ever approached? What undiscovered states of matter might emerge in the collision's crucible? These mysteries remind us that for all humanity's progress, the universe still holds puzzles that defy our models and ignite our curiosity. Every extreme event we imagine prepares us to recognize the real ones when they appear in telescope data or gravitational wave signals. This journey through cosmic destruction also underscores a deeper truth. The universe is a place of constant transformation. Worlds are born, evolve, and meet spectacular ends, their materials scattered to fuel new creations. Our own planet, with its delicate balance of conditions for life, is no exception, just one temporary masterpiece in an endless gallery of cosmic art. Contemplating the glass planet's fate invites us to marvel not just at its fragility, but at the resilience of matter itself, forever adapting to the universe's demands. As we close this chapter, remember that the best of science thrives at the edge of imagination. Thought experiments like this aren't flights of fancy, they're bridges to discovery, stretching our understanding until reality catches up. If you've enjoyed this dive into the cosmos's wildest possibilities, let us know what other extreme scenarios you'd love to explore next. The universe is vast, unpredictable, and endlessly creative, and together, we've only begun to uncover its secrets. Keep looking up, stay curious, and never stop wondering what else is out there, waiting to reshape how we see the cosmos.